All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.
Have you any time observed the wires hanging at your home? And when somebody shakes it. So there are normal pattern of some waves traveling to one place and coming back. Basically these are transverse wave. Hello everyone, I am Sachin Kumar. Welcome to S.chand Academy. And today in this lecture we are going to study about transverse waves in a string. Basically the waves can be characterized in two ways. One is longitudinal waves and one is transverse waves. So in case of transverse wave, the motion of the particle of the medium is perpendicular to the motion of the wave. So the wave is going in this direction, but the particle is moving up and down. In fact, the particles of this wave are not moving. On the other hand, take the example of longitudinal wave, the case when in the direction of motion the particles are moving. So acoustic waves or sound waves, in fact, you talk about them. So the motion in the particle is in the direction and they come back. So overall they oscillate in the direction of the motion of the wave. Now we are going to discuss about the transverse wave in a string. To read about this topic in full detail, you can refer this book by S.chand Publishing, and you can also find its ebook link in the description box. So let's come to the topic. First, if you have a string, what kind of wave pattern you observe? So basically a function point of view, from a geometry point of view, I am going to explain like what kind of function you will find at this place. So there is a string and consider I have a wall at this place. So if this string is making a pattern like this, so you just jerk this string and now this pattern is moving forward. So this transient, so this single pulse of force is known as transient. So this transient or this pulse is moving forward. So let us consider this has a function like this, which is fx, a general function, any function fx. Now this function is moving forward. So in case it is moving forward, so we modify this equation to an equation like this, where I can write it as fx minus ct. So x minus ct, because I am imagining like from 0 point this is going to positive x direction or the positive direction. So in that way I am writing it as x minus ct. Now what is this quantity c? C I can also write it as cs, which is the velocity of wave in this string, and usually t is the time period. As time passes by, so this is the place where the function is situated or where that pulse is situated. Now how this can be understood? This function x minus cst, how this could be understood? Just imagine like from this point, this in positive x direction, this pulse is moving forward. So let us consider this peak is at point 2 and this is moving at a speed of 1 unit per second. So 1 unit of x per second it is moving. So after 3 seconds it will move and reach to a place where its peak will be situated at 5, because in 3 seconds, so I am writing it as in 3 seconds it has moved, its peak has moved from position 2 to 5. Now if I consider this is function x, so I can write this function as f x minus ct, where t is 3 seconds, c is 1 unit per second. Now you can find that this function, consider it is explaining its peak at x equal to 2, and the shifted one is explaining its peak at x, which is 5 minus 3. Overall, the function is situated at x equal to 5, but minus ct factor is telling you that this is the same function which was at f2. So overall, you can consider this as a theory from the graph, or when you move forward in the positive x direction, in that case you transform your x to x minus ct, or x minus that constant factor, how much you are shifting in the positive x direction. And in case you are moving in the negative direction, you will write it as x plus ct. Fine. So all wave equations you will find of this pattern, of this shape, in which you will find a function of x minus ct or similar kind. Now let us come to the string. The transverse wave in a string also behaves like this. We have a string which is at its ground state at y is equal to 0. Now let us consider we just jerk it and somehow it is moving like this, so that we can say that okay, so this is from x to x plus dx part of this string, which has been shifted from 0 to dy. So there is a dy shift. So finally if I look at its hypotenuse, so just by Pythagoras theorem I can find that okay, this should be dx square plus dy square square root. So what is the length of the string when it is taking a new shape? Now this is equal to if I take dx common from this expression, so I will get 1 plus dy by dx. So the square of these and the square root. So this kind of expression we can see. Finally, by binomial expression, because we know that this quantity dy is very small, there is not any kind of discontinuity in the system. So this string is continuous and there is a small shift in that dt time, or we can say with dx, dy is quite small. In that case binomial approximation can be applied and you will get expression like this: dx 1 plus half dy by dx square. Because dy by dx is small, that is why we are not writing further coefficients of, because dy by dx is small, that is why we are not writing further terms of this binomial expansion. Now if you look at this, becomes dx plus half of dx dy by dx square. So initially the length of this string was dx, but what happened when you created a transverse motion, its length became dx plus some quantity. But just because this dy by dx is quite small and its square is even smaller and this quantity dx is even multiplied with this, we can imagine that okay, so should be some longitudinal motion as well, but we are neglecting that motion in this case. Now we are assuming that this string is remaining intact and moving as usual, it is moving with no length change. So it is so stiff like this that no change in length is observed when a transverse wave is passing through this. But this all is just about the peripheral description of a transverse wave through a string. What is its real equation? So we studied about the nature of the equation. We studied that okay, longitudinal motion can be neglected, but now what should be its wave equation? That we are going to study after a short break.
हाय, आई एम मनीषा सिंगला। इनऑर्गेनिक और ऑर्गेनिक के कुछ डिफ़िकल्ट कॉन्सेप्ट्स को आसानी से समझाने के लिए मैं आ रही हूँ S.chand अकेडमी में। तो अगर आप हमारे वीडियोस को देखना चाहते हैं तो सब्सक्राइब ज़रूर कीजिए।
Welcome back to S.chand Academy. Before going to break, we were discussing about transverse wave in a string, and we were just at the verge of starting its expression. Earlier, we just studied its peripheral assumptions and some basic things regarding that. But now, let's take an assumption in which we can assume that there is a string like this. So, which has already been shifted to a position in y, and obviously it is stretched, and obviously it is starting from x and ending at x plus dx. In this way we are just taking a small part of it. Now there are two forces basically acting on it, and we know that this tension force acts along the length. So in this direction at point x, I can find that okay, this should be the T1 tension, and at this length x plus dx, this should be the tension along the length of the wire. Now if I just take horizontal lines for my reference, so I can think that okay, this is angle theta, and this is theta 1 and this is theta 2. So these are two angles for tension 1 and tension 2. Now if I look at this picture, there is one force, one tension which is trying to pull this string down, and the another tension is trying to pull this string up. Now the force which is pulling this string down at the point x is T1 sine theta 1, and the force which is trying to pull this up is T2 sine theta 2. As we know that this shift is quite small, this theta is also very small. That's why we can write this as T1 into the slope, which is the tan of this angle. Because the theta is very small, only in that condition we can write this at this place. So T1 into slope at this point of the string can be written as equal to the force which is pulling down, and similarly the upward force is T2 into the slope at this place. Now if I just write it as a summary, so F net, so net force on this is overall equal to T y dash. So this y dash is situated at x plus dx minus the downward force which is related to y dash at point x. So, the slope at point x. Now, this is your net force, and in which because there is only one string and one force is applied. So, the tension in both cases will be equal, that is why we have taken it out. So, overall if I multiply this with dx and divide it with dx, so I will get something like this: y dash x plus dx minus y dash x divide by dx. So, overall T dx will be the quantity into, and this is the definition of the derivative. Overall we can write it as second derivative of y with respect to x. So, this is the term we are getting here. Now, if we extend this quantity force can be written in the terms of m into a. So, this quantity mass can be written as mu dx, because dx is the length of the string and mu is the mass per unit length. If you multiply mass per unit length with the length of the string, in that case you get the mass of that part of the string. Into the acceleration. So, acceleration is the second derivative of y with respect to t. Now, this is equal to t dx d square y by dx square. So, from right and left you can cancel out dx, and overall you will get mu d square y by dt square is equal to t d square y by dx square. This looks like the general equation to a wave, a transverse wave in a string, and if I just a little bit rearrange this, I can write this as d square y by dt square is equal to t by mu d square y by dx square. So, guys, this is the equation of transverse wave in a string. In a general equation, you will find that if you look at dimensionally, so basically at this place you have second derivative of y, at this place you have second derivative of y, here you have x, here you have t. So, dimensionally if you want them to be equal, here the dimension of this t by mu should be equal to the dimensions of velocity. So, overall the velocity of a transverse wave in this string Cs square will be equal to this quantity t by mu. So, we have just analyzed it dimensionally, and from that we have reached to one conclusion, and experimentally also this is also true. So, overall Cs is equal to square root of t by mu, where t is the tension of the string. So, how much the string is stretched, the faster the wave will travel through it, and mu is the mass per unit length. Overall, if the string is lighter in weight, in that case the wave will travel faster. The same pattern you can observe if you have just observed the guitar strings. You will find some thick wires, some thin wires. So, in the thick wires you can imagine the waves travel slowly. That is why its frequency is lower. And when you look at the fine wires, so the waves travel faster, and proportionally you can imagine that their frequency is higher, because in those strings also we play with the transverse waves only. So, overall in this lecture, first we started with a general equation of a wave, So, the general character is fx minus ct, this is the basic nature, any wave equation should follow. After that we came to a point, okay, there should be some longitudinal motion, but we are not going to take that because that is very, very small. And finally we reached to a point where we started discussing about the tension in the string and the net force F equal to ma, just by rearranging the facts and the derivatives. So, we got to the point that the velocity of this wave is square root of t by mu, and the equation. Any solution of this y in these equations, so it will be similar to the equation we have discussed earlier, like f x minus ct. So, everywhere you will find a function like x minus ct, because as time progresses the wave will move forward. So, in this way a transverse wave can be studied in a string. To read about this topic in full detail, you can refer this book by S.chand Publishing, and you can also find its ebook link in the description box. Please don't forget to like, share and subscribe to this video.